Okay, let's check you can hear me. Great. So my task right now is quite modest, as if my earlier task wasn't modest enough. I want to present a very simple-minded, naive, plain, poor man's view of Strassen's matrix multiplication as kind of my way of revisiting it. I will present two equivalent formulations for that method, and I will actually analyze its complexity from scratch. Just for fun. It's very simple again, but maybe people have not seen it. And surprisingly, even if you do search on complexity of matrix multiplication, most people on YouTube who talk about this just wave their hands around. So perhaps it's worth it. And I will say a few words about other problems that are reducible or essentially reducible to matrix multiplication in the sense of their complexity. And maybe I'll say a few words about issues that are related to what I talked about in the morning, so time permitting. And I realize I'm under more stringent time constraints right now. So let's try this. Okay, so let's revisit Strassen again. And I'm going to be extremely annoying in that I will actually write this down. So bear with me. Okay? So I will pretend for now that we are actually dealing with 2 by 2 matrices as such. And then we'll see how it lifts. So let's say we have a matrix A, which I'll write explicitly. Okay? So don't worry. A11, A12, A22. We want to multiply it by another square 2 by 2 matrix B, B11, B12, B21, B22, okay? And when we want to get the product matrix C, which we'll write as usual, C11, C12, C21, C22, okay. And Strassen, after, I don't know, some divine revelation, or probably working his butt off, I suppose, got to 7 multiplications instead of the expected 8. So first a word about the classical multiplication. If you start multiplying matrices the way everybody is taught initially, you will have to commit to 8 scalar multiplications. Why 8? Where do they come from? Because to compute each entry in the product, you need to perform exactly 2 scalar multiplications. Actually, there is an extra addition that goes there. So you go 2 by 4. That's 8 scalar multiplications. Scalar means a scalar value times a scalar value. Nothing fancy is going on, right? Plus addition. So you'll get whatever the total amount will be. So Strassen realized that you don't have to do 8 multiplications. You can reduce this procedure to 7. At the additional cost of extra additions and subtractions, but this turns out to be beneficial for the asymptotic rate, for the sort of performance of this algorithm for large values of n, and we'll get to this in a sec. Okay, so the values Strassen realized were useful were the following products, and I'll write them down extremely, in excruciating detail. So first you perform this sort of multiplication. Then this is your M1, your intermediate value M1. Then you go M2, which is going to be a variant of this. Then you go M3, well, there's 7 of them, as I promised. A11 times B12 minus B22, okay? Then you go M4. This is A22. B21 minus B11, okay? We're almost there. M5 is A11 plus A12 times B22. And then a couple more. Here we have M6, which is going to be A22 minus A11. There is a reason why I'm writing this, so not just to show that these are the formulas. And finally, M7. which is gonna be A12 minus A22 times B21 plus B22. Okay? So it turns out that these 7 intermediate products are enough to reconstruct C linearly. So these are not yet the values of C, but you can combine them linearly, and in fact, just by adding and subtracting those values, you will get to the values of C. How do you get the values of C? To be precise, so you need 4 of them, right? So C11 will be just M1 plus M4 minus M5 plus M7. So it's this sort of combination. C12 will be M3 plus M5, I believe. C21 will be the other way around, the even ones, M4 and M2, so M2 and M4, okay? And then the last one, C22, will be M1 minus M2 plus M3 plus M6. And the first homework assignment for this lecture is to verify that all of this works out. Let's just check the simplest one. So there's a couple of sums which are kind of simple, right? So maybe we'll check one of them. Well, let's look at M3 plus M5. That shouldn't be so bad, right? So what's M3? This is M3, and this is M5. And now you see where the cancellation will occur. The cancellation occurs in what terms? So something here will come with plus, and something from the other term will come with the minus sign. So what cancels what? A11 and B22, right? A11 and B22 is present in both of these, but with opposite signs, so they will be gone. And what you see is a perfect sum, which we need for the entry that was claimed here, right? C12, because that should be what? A11, B12 plus A12, B22, and that's perfect. That's exactly what it is. So the others are a little bit, but this is exactly that much work, and then the others are a little bit more work to verify. Okay, now let's just stare at this for a bit and then start kind of seeing what this is about. So the first thing that you might notice is that this is a bilinear algorithm. Okay, so what on earth does this mean? That means it's linear separately in the entries of A, right, and in the entries of B. How linear is linear? How should you think of this? You can think of A not necessarily organized like that. This is all, right, this is just the form. You can think of it as being organized as one long vector, if you prefer. And basically, as an action on this one long vector, this is a linear action. If you think of B as being fixed, right, so pretend the B's are staying fixed, and the A's can change linearly, that is, you can combine 2 such long vectors as a linear combination of these long vectors, right, and the reflection on the outputs here will be linear. And then likewise, of course, here, because all these operations are linear. Right? And then likewise, if you keep A fixed, all the entries of A are kept fixed, and then perform a linear transformation on B in the sense of the totality. So I'm not worried yet about B as a matrix. I'm just thinking of B as a vector object, right? So you can vectorize it, so to speak, right? You can transform it into a single vector if you prefer, but you don't have to. You can just think of this as data, right? And so if you transform this linearly, if you form a linear combination of 2 objects like that and plug this in and keep the A part intact, then your result will be transformed linearly, right? So that's a bilinear algorithm. So that's not a coincidence, as a matter of fact. You can say, well, that's how the matrix multiplication is defined in the first place. If you now examine the matrix multiplication formulas 101 that we were taught initially, they are also bilinear, so that's not a surprise. And in fact, there is a result which is due to Ran-Raz showing that, without loss of generality, if you got a fast algorithm that somehow manages not to be bilinear for the matrix multiplication problem, you can always convert it to a bilinear algorithm, basically without loss of your complexity bound. And I'll talk about complexity analysis in a bit more detail. Right now I understand this is very hand-wavy. Question?
So formally a bilinear algorithm means that every intermediate computation is bilinear?
Yeah, that is correct, yes. So, if you want to formally define a bilinear algorithm, then you say, throughout, so you can represent it as a computational graph, as a where you label the vertices with every operation. So technically, right, you can insist that every operation there is a bilinear operation, exactly. And therefore, your output is also bilinear, but yeah, it's a more strict requirement. So throughout the algorithm, everything is bilinear. Perfect, yeah. Cool. Okay, any other observations we can make? So let's try to run the complexity analysis on this. And it's going to be quite basic, but it's very illuminating, showing us what can happen, right, in this scenario like that. So first of all, what you notice, before we proceed to analyze complexity, is that this is written all in lowercase. All the A's, B's, and C's are in lowercase. However, we can bump them up, right, and convert them all to uppercase. And this is not just a matter of calligraphy. So what am I after here? So if we transform all the lettering from lowercase to uppercase, so what would that tell us? What's going to happen?
Block matrices.
Block matrices, great, right? So notice that the cancellations will still occur because the cancellations are not due to something being equal to something else as scalars, right? So we actually have things listed exactly in the right order. Everything in the first factor is always just some combination of the A's. And everything in the second factor is just some linear combination of the B's. We just talked about bilinearity here, right? So in other words, if we convert everything to uppercase, and now think of this not as a 2x2 matrix, but as a 2x2 block matrix, then everything will still apply, okay? So in other words, and that's what Strassen, of course, noticed right away, this algorithm applies recursively, okay? Now, so in other words, if you have a square matrix of size n by n, you can now reduce it to a square matrix problem of size n over 2 by n over 2. And then there is a pesky issue here, which you already obviously identified, I'm sure. So what's the pesky issue that you might think is an obstacle, is a problem?
N is not a power of 2.
N might not be a power of 2, right? In other words, even if you start with n being even, then you're lucky n over 2 is okay, right? Still an integer. But then proceeding beyond that, below that, right, could be a problem, and then you can theoretically get stuck. So how do you overcome the issue of n not being a power of 2? Zero padding. Okay, great, right? So you guys have seen this. If your size is inconvenient, if the size of a matrix problem is inconvenient, and especially theoretically you want to prove something, some complexity bound, ideally, right, you can always pretend that your matrix size is a perfect power of something, in this particular case 2, by just throwing in a bunch of zeros and pretending it's a larger matrix with this bunch of zeros thrown in. Okay, so let's pretend, yes?
Sorry, this might be obvious, but like, if I had come up with this list of multiplications, like, is it obvious that I could have reordered them? Or there have been like some list of.
Is it obvious then what? That
like,
what?
It's important that all the A's appear first, so then when I move up to matrices and they don't come.
It is important here, right? If you wanna lift it to matrices, yeah. If you want to lift it to matrices and apply recursively, then it's important that these relations, right, remain valid when you replace single entries by matrices. So yes.
I guess what I'm wondering is.
I mean, there are, so just to anticipate your question, there are methods where this does not happen, and then it becomes a headache and you have to deal with this. So maybe Oded will mention something about these methods in his talk, but that's not my purpose right now because I'm only doing the most straightforward stuff today, if that's okay. Okay. All right, so cool. So let's just run the cost analysis, so to speak. Okay, so what is our complexity assumptions? Very simple. We will be just counting, as our complexity measure, we'll be counting all operations. And we will think of them all as being equally expensive or equally, whatever, inexpensive if you prefer, right? So I'm not distinguishing between multiplication and addition or multiplication and subtraction. I'm not distinguishing subtraction from subtraction, addition from subtraction. I think that of them all as equal, but you will see that naturally this multiplicative complexity will arise. And that hopefully will answer some of the questions as well that were lingering perhaps after GAM's talk. Okay, so let's just do the cost analysis very, very simply. So we will say, for simplicity, and that's, as we already said, without loss of generality, n, our matrix size, so our matrices are n by n, okay? And so n, our matrix size, can be thought to be a pure power of 2, okay? And let's just run the analysis here. Okay, so if we now lift all of these two matrices, then the cost of running this algorithm at size n is going to be what? How does this compare to the cost of running this at size n over 2? So we've got 7 multiplications going on, right? They will be converted to what? They will be converted to 7 matrix multiplications, right? At the size, what? Of matrices equal to n over 2, right? So in other words, t of n is 7 times t of n over 2, okay? And that accounts for our recursion step. Okay, that's not it. What else is there? Then we need to do all of this stuff, right? So we're not just multiplying 7 matrices. Within each factor here, we will do some algebraic stuff, additions, well, linear algebraic stuff, right? Additions and subtractions, and so, and likewise here. So I will be lazy, and I will just say all of this, it's going to be a very specific constant, and Oded is the world specialist in constants, so go talk to him. He knows what the number here is. What's this? 18, I think, right? So here you get 18 times n squared, correct? 18?
N over 2 squared.
The dimension half.
N over 2.
Oh, you're counting in n over 2.
N over 2 squared.
Yeah, because
Blocks
you're
are-
doing it at one level down. So it's N over 2 squared.
Okay, yeah. Well, whatever it is, as you can tell, I don't care too much.
Exactly.
You're right, right?
But it's better than
It's better. Well, certainly it's better. And Oded will testify to this in his talks. This is certainly better. So n over 2 squared, right? Okay, but I'll just call this whatever. I'll just call it constant c. Okay, so whatever it is, I mean, we got 18 over 4, great. But I'll just call it little c if you prefer. Okay, I can run this with this particular constant if you like. Let's do this, it's okay. Okay, so if we start unraveling this thing, let's just perform one more step so then we'll start seeing the pattern here. So, okay, so if I do this one more time, I go 7 times what? And now I will unravel this using the same formula, right? So I can then say it's 7 times what? T n over 4 plus, again, to be specific, 18 times n over 4, right, squared, okay, plus this one, 18 times n over 2 squared, correct? Did I miss something?
N over 4 squared.
This is n over 4.
No, the next one, 18.
This is
No,
18.
to the
The
right.
second one's still N over 2.
This is still this. I'm carrying this. I'm carrying this.
Oh, that's left over.
That's
from the
left over. Yeah. We should not discard it, right?
Yeah.
It's not like we are suddenly skipping terms, right? So this is still there. Okay, cool. So imagine this keeps going until we reach our base level, and your choice of base level could be 2, or it could be just 1. All right. So if we pretend we go all the way down to 1, right? So we did this a bunch of times, then what are we going to have? What are we going to collect? We are going to collect 7 to some power times t of 1, let's say the cost of doing it for 1 by 1 matrices. So what power of 7 should I use here? M, okay, right? Times t of 1. Okay, and what about the rest? What is happening here? So we'll have 18 in all of this. We'll have n squared in all of this, right? 18 n squared. And then the rest will be what? A geometric sum. Correct? So what kind of geometric sum are we going to collect? It starts with a quarter, right? Or 1/2 squared. Then we go 1/4 squared. And how far do we go? We can pretend even we go to infinity if you'd like.
1/4 squared times 7, right?
Pardon?
1/4 squared times 7, right?
1/4 squared times 7. Yes, yes, thank you. We should not drop the 7. Where is the 7? Good catch. Yeah, so it's not just this. Plus 7 times that factor, right? Plus 7 squared, the next one. Let's be honest and write this down. Plus 7 squared times what? There is 1 7 here, the second 7 here. This will be 1/8, right? Squared, and so forth. Okay? You can go to infinity or not. Let's see. So actually, let's be precise. So what's the last term here that I should put? We can do 2, yes, instead of 4.
No, 2 to the m instead of n. Well, 2 to the 2m.
We'll get to this in a sec. Don't worry. What's the last term?
7 to the m.
7 to some power, right? And 1 over some power of 2 squared, right? So what should I put here?
2 to the m on the bottom.
So 7 comes up with what powers? So here,
-1, I think, right?
m minus 1, I guess, right? M minus 1. Okay, and what's the power of 2 here?
No,
Oh no, 2 to the m.
M.
So let's just rearrange this. So it's 7 to the m minus 1, right? Over what? 2 to what power?
2m?
To the
2m minus
2 to the 2m.
2m, right? 2m. We agree on this. Okay, 2m. Cool. 2m. Okay. So what does it give you? T of 1 is maybe, I don't know, 1? Again, whatever it is, it's a very modest constant, but let's say it's 1. So what is 7 to the m in terms of n? So this analysis gives us what? 7 to the m in terms of n. N is 2 to the m. So 7 to the m, basic logarithms, what, 14th century?
Log 2 of 7.
7 to the m, actually,
N to the
n
log.
to the power log base 2 of 7, right? Times, so n, so 7 to the, this is n to the power log base 2 of 7. Okay, cool. Okay, and what about this stuff? We have this geometric progression, so let's just rearrange. 18n squared. We have 1 minus, what's the ratio of this geometric progression? 7 quarters, I suppose, right? 7 quarters is the power that gets repeated, 7 quarters. Okay, and what do I put here? 1 minus 7 quarters to what power? It's not exactly 1. There will be a 4 here as well, right? So 1 minus 7 quarters to what power? Roughly m. Is it m?
M minus.
M minus 1, one of those, right? M minus 1. Okay, cool. So the leading term here, this is a constant. This is certainly a constant. This is a constant. Here's n squared, still lingering. And so what is 7 quarters? So basically we just need to understand 7 quarters to the power roughly m. What is this? 7 quarters to the power m. Well, we already know what 7 to the power m is. This is n log base 2 of 7. And what is 4 to the power m? This is
N squared.
n squared. Cool. All right, right. So this is n squared. And we already had n squared. So the n squared terms will be gone. And so what we see is another term of the same order. And again, I'm being kind of lazy with constants, but what you see is a constant times n to the power log base 2 of 7. And that was the punchline for Strassen and for us as well, right? So we see a term, so basically a constant, big O of n to the power log base 2 of 7. And then you can see that the costs of doing this recursion or doing any recursion like that are dictated by this magical value here. Right? So if you somehow are very lucky and can reduce this further, and then you run the same analysis, which is, by the way, what they call the muster theorem in computer science. So that's a basic observation about any sort of recurrence that works this way. Then you will see that this magic number, right, together with this factor reduction number that will occur, together will give you this logarithmic value which determines the exponent of your method. So the exponent of Strassen's method is log base 2 of 7, as we demonstrated. Any questions on this
I have a
basic
question.
part? Yes, please.
Is the 18 known to be optimal? I presume 7.
It's not optimal. And you should come to Oded's talk, who will optimize the hell out of this method. Okay? Just a preview, Vinograd modified this method by reducing this number 18 to the number 15. And for a while, that was the record. Then there was further reduction to 12, and this was shown to be optimal. But then Oded can do better than this, and you can say, well, how is that possible? Somebody must be lying. And he'll tell you how this is possible. So the magic is to happen then. I'll not spoil the details. I'll hint at some of the details, but I'll not spoil them. Okay, let's look at this method from the tensorial sort of perspective, and this will be, as I said, a very naive, low-key, super simple interpretation of tensors. So no secant varieties will be harmed in the process. And
Use those words in the talk.
okay, all right. Anyway, so let's look at this, and I will write this. So remember this inscription here, right? So we actually wrote this down. So I'm going to bring out this tensor business. So why tensors here, right? So where on earth do we get those tensors, and how can we think of this? And remind me what my ending time is? What's my...
5 minutes late, so we'll end at 3:05.
3:05. Okay, so I better be quick. Okay, so where are those tensors? So first, I'll just introduce tensors as a purely bookkeeping device. Okay, as a purely bookkeeping device, we'll get an n squared by n squared by n squared tensor. So how? And then again, think about 2 by 2. So our base case is n equals 2. So just think about 4 by 4 by 4, 3D tensor, right? So i.e. here, for Strassen, let's go back to the basics. So 4 by 4 by 4 tensor. Okay, so what does it look like? So it's, think of it as a three-dimensional array where in each direction, we are going to index things lexicographically. So why? Because we have pairs of indices in the original matrices, right? So those 4 entries will go like, well, for example, 1, 1, 1, 2, 2, 1, 2, 2, right? In each direction. And so think of this little tensorial sort of entries. The tensor entries will be basically just little slices. So there are 4 slices like that. They're all square, so excuse my drawing, it's atrocious, but okay, so it will look like this, okay? And so for example, I just want to label one just to really understand what's going on, one more, okay? So let's say we go here, and this is being labeled A11, A12, oops, A12, A21, A22, or maybe the B's, whichever you prefer, right? And here we'll just say B11, that's a slice. And then this direction will be labeled by the C's. You can choose how to label this, it doesn't matter, okay? So again, I'm not concerned with fancy invariants here, so bear with me. C11, C12, C21, C22. Okay, so as a pure bookkeeping device, I want to indicate which entries will actually contribute to the to the resulting product, okay? In other words, I want to say, to compute this entry, I need to use a specific product of the A's and the B's, right? Per the standard formula. This will contribute to this specific result. So a lot of them will not contribute. I'll just leave them this kind of picture blank. Okay, so which entries will not be blank in this little slice? How many? Be careful. Two, right? Because this is just the slicing for what? B11. So there are just two products that contribute to B11. Which ones? A11, C11. So maybe this was a bad choice, right? So we could have flipped this around. But anyway, right? What is this? C11 will come out of this. And what else will come out of this? C21, right? C21, we all agree, right? C21 will come out of this. Okay, so where are they in this little slice? I'll just kind of shade them. The top box, right? The top box is here, so this little square will contribute. And what else is in here? A21, C21, and where is this? A21, C21, it's right here, right? What is this? A21, pardon me, yeah, I got the wrong one. A21, this is still unshaded. Oops. So A21, right? C21, so it's here. I hope I got the right one. Okay, anyway, there are two of those. Okay, cool. And then in each slice, there will be actually the same number, right? The same number of shaded, used entries and unused entries. So you can think of this as just a bookkeeping device. Alternatively, you can also think of this, and I don't think we've seen this, but that's a helpful way of thinking about these operations here. We can think of three auxiliary matrices consisting entirely of zeros and ones. They're actually secretly being applied to our input matrices A, B, and C, and I'll explain in a sec. So what's going on here? We have U, which is 1, 0, 0, 1. For example, 0, 0, 1, 1. I'll just write a few of this down, and you'll see the method to this madness, okay? So 0, 0, 0, 1, 1, 1, 0, 0, minus 1, 0, 1, 0, 0, 1, 0, minus 1. And there is a similar matrix, so this is a 4 by 7 matrix. There is a similar matrix V, which is 4 by 7. And there is a third matrix W, 4 by 7. So what on earth am I doing here? What am I recording, and how is this relevant to what is on the leftmost board? So what is this matrix actually recording? This is sort of the meta matrix here. Yeah. What does it do?
The additions for A.
This is, yeah, exactly. This guy records all the linear operations, right? All the additions and subtractions we have to perform on the A part, right? You can rearrange this if you prefer tall and skinny matrices. You can think of them as directly multiplying this vectorized version of A, right? So if you convert it, right, to a tall skinny and say, okay, what is this? 1, 0, 0, 1. Okay, where is that? The first entry comes with 1, right? The second comes with coefficient 0. The third one comes with coefficient 0. The last one comes again with coefficient 1. So this is actually the encoding of this little factor. And then likewise, right? So we just listed all of them. And then in the same fashion, you can write the matrix, the so-called matrix. They're traditionally called U, V, and W. Don't ask me why. I don't know. So you can write the similar matrix for V, and you can write the similar matrix for W. And what does W do? W will tell you how to decode stuff right here, okay? So your second homework assignment is to write these guys. So what is V? What is W? For the classical Strassen's method, okay? And now you can see 7 here. So 7 here is actually in this kind of poor man's matrix, meta matrix interpretation. What is 7 here? just the number of, like, depends on how you want to organize this, are either columns or rows. So here we organize them like that. Usually in papers, it's just easier to type them this way, right? So they're kind of sitting that way. Okay, so 7 is just the number of columns, or alternatively, if you prefer the Tolkien version, the number of rows. And so 7 is exactly the rank of this magical tensor whose slice we just kind of glimpsed here. Okay. Now you can see why the tensor rank, I'll try to motivate this to the best of my ability. Okay, so what's going on and why tensor rank? So what happens here if you have a single linear form, right? Multiplying a single linear form, and this will give you, right? So it's a single product eventually, right? It's a single product, and this single product allows you to compute the result by linearly combining a bunch of such products, right? Using these operations, this sort of decoding operations, okay? So likewise, you can think of this whole cubic, like 3D tensor as, so think of every tensor decomposition. This is a direct tensor decomposition in disguise, actually. Like this is this one way of looking at it, where you can just look directly on the tensor, right, and see that. So whenever you split a three-dimensional tensor like that, matrix multiplication tensor, into this exterior product in 3 possible directions, what does it mean? It means take a linear form in A, multiplied by a linear form in B, like that, like something very concrete, right? And this gives you a linear form in C, and if altogether you sum this up and you get the original tensor, that just means you can combine them like here, right, to get all your entries of the answer. So this is sort of the naive, very basic explanation that I would suggest exploring. And then, I mean, that's probably homework. Just stare at this and kind of see how this lines up to actually correspond to tensor decompositions here. Okay. So I wish to say, so again, do attend Oded's talk, because he can do further magic on this matrices, U, V, and W, and get some amazing stuff. And I'll just conclude by saying a few more words about this problem. So Strassen, of course, now has improvements over this original result. Some of this is due to Strassen himself. Some of them are due to many, many other people who worked on these methods. And there is a whole family of Strassen-like methods now. They are all kind of like this. Some of them are not based on a square base case. Some of them are based on a rectangular matrix multiplication case. And that's another sort of kind of homework problem. So suppose somebody gives you a base case, let's say a modest base case, which is not square, but rectangular. How would you modify this whole process, just specifically algorithmically? Forget about the complexity bound, although you might want to run that too, right? So how does this give you a recursive method if your base case is not square? What would you do? How would you run this? Just kind of entertain this possibility. So it's not exactly a homework assignment, but just something to think about. Okay. And another thing that I want to say is that there is a whole family of matrix problems which are reducible, or so to speak, essentially reducible to the problem of matrix multiplication. And here I just want to mention matrix inversion. And again, you can explore things beyond that. So for matrix inversion, we can start with a basic observation, which, where is this? Which tells you that a reduction is possible at least in one way. And then we have to work a little bit harder and perform complexity reduction the other way. So just to show you one complexity reduction, which is really simple. Okay, so matrix multiplication is as costly, right? As costly as matrix inversion. Okay, how do you prove something like that? Oh, okay, let me move over to.
Yeah. Oh, yeah,
It's on the screen.
yeah.
I can move over if you'd like. Yeah, let's just, so I don't think we need the formulas now. I'll just indicate how this complexity reduction can be done. Okay, so let's say you want to invert something very straightforward. So it's a block matrix with identities on the main diagonal, so you can already say there is not much to invert. But then I want to be sneaky because I want to get matrix multiplication somehow out of this. So what should I say? I want to invert something where I get my A matrix, and I can just use 0 here, right? And B in the second block. And I suppose I want to invert this. What would be the formula for this? We can all do block inversion, I think, hopefully, fairly straightforwardly here, right? It's a block triangular matrix, so identities still sit on the diagonal as we invert. Okay, and what happens here? What should I put here? Minus A. Okay, so that's not the interesting part. Here, what happens? That's also not super interesting, right? What do I put in this in minus B? That's not interesting. What is interesting here?
AB?
AB, right? AB occurs here. Okay, so actually, what does it say? If I have a pair of n by n matrices and I organize this block matrix of size 3n by 3n, right, and invert it, it will look like this, where the product will naturally appear. So how does it show? What kind of complexity reduction does it show, therefore? If I can do something at a certain rate, then I can do which problem? So which way does it go? If I can do inversion at all, right? So it's some, you know, if I have a complexity bound on inversion, then I can put this particular matrix there. I just need to triple the size, correct? And then automatically that procedure will give you matrix multiplication for AB. And you can see, well, there is a tripling of the size, but since here we are being generous and we are only concerned with constants, it will not affect the complexity bound that will occur, right? So that's the inversion to matrix multiplication reduction. So if that is possible at a certain rate, then multiplication is possible at most at that rate, right? And how do you go backwards? Going backwards is a little more complicated, and this requires a little bit of Schur complement and other stuff. And so I have it on my cheat sheet just in case I don't manage it. So now, if you want to do something, so if you want to invert x, you don't do it directly, but instead you perform some contortions, right? So instead you write x as what? As, or let's call it still, yeah, we can call it x, right? So I want to do the inversion of x, but I want to do it differently. So how would I invert it differently? I want to manufacture a symmetric matrix, right? And then I want to invert it. So what should I do?
Transpose X?
So if I do, let's do this. So that's okay, right? X transpose X, and I invert this. Then I will get X transposed inverted, right? So I should actually flip everything. So let's do this. That's okay too. So I should put the transpose where we didn't have the transpose, right? And I should remove the transpose where we didn't have the transpose, okay? So you can say, what does it buy me? So we do have a matrix multiply here, right? This is already a matrix multiply. But with that, we still need to invert. But there is an advantage to inverting this matrix, because that's now a symmetric, actually totally non-negative matrix, totally positive matrix, because we assumed X was invertible. Okay? And then to invert this, you perform the trick, the divide and conquer trick, and then recursively analyze this result. And you need to use the Schur complement in the process. So let me write this down. So if you want to invert something which is symmetric, you can use the following trick. And that was on my cheat sheet. Okay, so you go like this. And I never remember this formula, so I'm sorry about this. You go like this, A inverse, B, S inverse. It's a lot of stuff. B transposed, A inverse. You can derive it, but in the interest of time, I'm not doing this. There is space here. Sorry about this. Of course, there is Wikipedia page for everything, yes. Minus A inverse B S inverse minus S B transpose S inverse. And here you have this S inverse. And S is the sure complement that will occur here. So S is going to be C minus B transposed A inverse B. Okay, so in other words, there is a reduction of this inversion problem to a smaller inversion problem for the sure complement, which is again going to be symmetric. And that's the thing. And by analyzing this and now using a bound on the matrix multiplication, you can get a bound of the same order on the inverse.
Why didn't you want to do Gaussian elimination to invert?
You can do Gaussian elimination to invert, but I just want to do a complexity reduction from one method to the other.
Gaussian elimination is a sequence of matrix multiplications.
It's a sequence of matrix multiplications you need to generate, right? So this is so yes, it is a sequence of matrix multiplication, but it's not just a couple, right? Or a bounded number. So you see my slight difficulty here. Here, here it's an exact number which is concrete, like however many here, 1, 2, 3, 4, 5 factors, right? So this is under control. If I do Gaussian elimination, you can be sneakier than that. You can, and then Jim will tell you what to do. Yeah.
This also only squares the condition number, which only doubles the bit complexity of your individual arithmetic operations. So that's nice to
Right.
like Gaussian.
Right.
But you couldn't you do Cholesky factorization recursively by 2x2 blocks once you've got the symmetric positive definite matrix, and then Cholesky would again be log n levels of depth, and it would come out about the same.
So you can reduce complexity in other ways, right? So there is another path, right? You can say we can do LU or LUP, whatever decomposition, where you decompose your matrix into a lower triangular and upper triangular and a permutation matrix, and then you can show that that also does not increase your costs, and then you can proceed through that. So just a word again, this is a little bit of a homework assignment. Check how check first of all that the formula works. The formula comes from such a block split, such a block decomposition itself, right? And then check that this works, and then see how you can use this recursively to actually bound the complexity of inversion in terms of the complexity of matrix multiplication.
Can you just a little bit describe the recursive step? Like, for instance, can you just say what size is A and S? Like, are we?
So you can do it even with a 1x1 block to begin with, or you can split into 2 equal blocks, which is better.
If you want to hit the complexity bound.
If you want to hit the complexity bound, right. So actually, yeah, play with that. So if you want to hit the complexity bound, the split is the even split that will work. But you can see, this is still true whatever you do, right? So just the formula holds however you split, but then if you want to run the complexity analysis, yeah, you want to split equally. Any other questions? Yes?
If I remember right, there's an algorithm based on minimal polynomials, right? Maybe that's costlier, I'm not sure. You can just write inverse of A as a sum of powers of A, but you have to pay for computing.
But then you need the minimal polynomial. You need to divine it somehow.
Yeah.
How do you get this? So again, this is like the simplest sort of reduction. You can also analyze the complexity of finding the determinant and show that asymptotically it's the same thing. But I'm sweeping a lot of details here under the rug, so it always depends on what you already have, and then you can use it, of course, right? But I just went for the simplest sort of reduction, which is, yeah, the minimal polynomial, nice to have it. Yeah.
You can find more details in our 2008 numerical mathematics paper that Olga and I wrote on fast linear algebra is stable.
Right. So maybe a word of this. Yeah. So incidentally, speaking of stability, right? So people wondered how unstable these methods would be because Strassen already scrambles those entries of A and scrambles those entries of B quite a lot. And you can say, well, do we have any hope of stability? And in this paper, so we have an initial paper which is called Fast Matrix Multiplication is Stable, which came out of our attempts to understand and use the group theoretic approach to matrix multiplication, and then generally all bilinear methods for matrix multiplication. And so that paper shows that all bilinear methods for matrix multiplication are numerically stable under some very mild assumptions and produces error bounds, and these error bounds are in terms of matrix norms. So they are not component-wise. Speaking of what we said earlier, this morning, but they are norm-wise. But then still they are effective if you want to be. Basically, that's the best you can hope for because the matrix entries are going to be scrambled quite a bit. And then there was a subsequent paper called Fast Linear Algebra is Stable, which talks about all these other methods which are the same or asymptotically the same in complexity as the matrix multiplication. So I guess I should stop here, and thank you again.
Thanks, Olga. Well, I mean, we had lots of questions during the talk. Maybe we can take questions or we can take one question.
You can take one or two.
Thank you. So usually when we do recursion in practice, we only do it at several levels to avoid and then just directly solve it as a base case. So I'm wondering whether it was possible that this kind of abstract inversion in each time we need to recur down to 1-1.
This is a good question in practice. So in theory, remember we went all the way down to 1.
Yeah.
In practice, you don't need to do this because it doesn't buy you anything below a certain level. So there is a magical threshold below which you just do standard matrix multiplication and you're okay. And so again, Jim will probably know where this stops, or Odette will know where it stops. So what's the practical kind of good threshold?
Practical threshold.
Well, I mean, you can do Strassen even for 500 by 500 matrices or so, like 1,000 by 1,000. It's still worth it, but then you only do a couple of recursion steps, and then at some level, I don't know, like double-digit level, you can do standard matrix multiplication. That's my understanding of what happens in practice.
The vendors have all optimized the classical matrix multiply, to run as fast as possible on the platform. So it depends on how good their library is when you switch.
Yeah, so it very much depends on what is already available.
They're all building special hardware accelerators for matrix multiply that also do the NQ algorithms. And when there's new hardware accelerators.
Yeah.
So is there any formula for this threshold? Like, is it generally increasing with respect to the matrix size, or
it's empirical?
Empirical. Okay.
Yeah.
No, it's not adaptive to matrix size. You just go down to a certain level and then you implement the matrix multiplication. It depends on your hardware and software.
So it doesn't necessarily grow with the matrix?
No, you start with a matrix of some large size or reasonably large size, and once you hit the threshold, which is non-adaptive, it's specific, then you convert to standard matrix multiplier.
Sure. Thank you.
Cool. Other things?
Okay.
You mentioned there's a theorem that says that you can always turn like a non-bilinear algorithm to bilinear algorithm. Is that like strictly bilinear? Like, is there any case we might have a U with all zeros in a column with all zeros?
So I need to look at the exact assumptions used. I remember the result being very general. It's in the Runraz paper of 2006, I believe, or maybe 2003. So it's some very basic assumption that you can convert. So he talks about arithmetic circuits, and if you're computing a bilinear formula, using the circuit, you can you can basically change the circuit and make it into a bilinear circuit.
I think this result is much older. It's also
And yeah, there are precursors to
He
this.
wrote a paper that you can read. It's called Vermeidung von Divisionen
Okay.
in German.
Yeah.
And that's where he...
So who, Strassen?
Yeah. Yes.
Oh, but everything goes back to Strassen, yes.
Because he wrote it in German.
Yeah.
Many people struggled with it. But then he shows that whenever you have like an arithmetic circuit or it's called straight line program, computing plenty of bilinear forms, then without loss of generality we can assume it's
Oh, fantastic. So, Vermeidung der Dimensionen.
well, actually not. Yeah, it's not. Sorry? Vermeidung von Division.
Von
I think the
Division,
main
yeah, okay.
point of that paper was that if the algorithm was also allowed to use divisions, like Gaussian elimination does, and then he showed you can get rid of it.
Of divisions
I think
as
that
well,
was the
yeah.
main
Oh, okay,
thing.
so it's there too.
That
Okay,
is
yes,
But
fantastic.
this is really the
Yeah.
justification why rank is a good complexity measure. And Ran Ra's paper was a more general framework.
Right, so it's not just about matrix
But of course
multiplication, it's
speaking
about other things. Yeah, yeah, cool. So our last homework is learning German and reading this
Even
paper.
today, well, I don't know whether it's still useful. Yeah, it's
I think the
nice.
instruction to reading some of Strassen's papers is not the language they're written in.
Okay.
Well, it's in your book too, right?
Okay.
Great, no, thanks a lot, Olga. So, 10-minute break, and then we come back for embarrassing questions which are not being recorded.
I don't